This video is from Carnegie Learning, Module 3, Topic 1, Lesson 1, about dilations. Now, I'm recording this video because I'm missing class, but I will likely post this in places, and so if you're watching this not during class, then go ahead and pause the video when I ask you to. Think about things that I'm asking, but if you're in class, then pause the video, discuss when I ask you to discuss. Anyway, after that's been discussed, you can then play the video again, and hopefully it simulates something similar to what we would do if we were in class. So this video, by the end of this video, you will talk about the definition of a dilation, what similar means, not just, hey, these things are similar to each other, but geometrically similar. And we'll also define similarity transformations that produce similar figures. Okay. By the end of this video, we'll talk about how to find the scale factor for a dilation. We'll also determine if two figures are similar, geometrically similar to each other or not. And finally, we will use similarity transformations to map one figure onto a similar figure. So the first thing we'll do is this question, okay? If x is greater than 0, can 4x be bigger than 4? And if so, when does that happen? And the second question is, can 4x be less than 4? If so, when does that happen? Okay, pause the video and discuss this in groups of 2s or 3s or 4s with those around you. Ready, set, go. Okay, so the first question, can 4x be greater than 4? The answer is pretty easy. The answer is yes. Okay, 4x can be greater than 4. If so, when? Well, it's true whenever x is greater than 1. So like 2, for example. 4 times 2 is 8. 8's bigger than 4. If x is 3, 4 times 3 is 12, which is bigger than 4. Okay? Any number bigger than 1, then you would get a number that's bigger than 4. Okay, now at first glance you would say, well, no, 4x can't be, for the second question, you would think maybe 4x can't be less than 4. But if you think about it long enough, you'll realize that yes, 4x can be less than 4. And when does that happen? That happens when x is between 0 and 1. Like 1/2, for example. Half of 4 is 2. And 2 is less than 4. Or 1/4 of 4 is 1, and 1 is less than 4. Okay, now that, in my mind, prefaces an idea we'll hit later on as far as when numbers get bigger and smaller. So I want to kind of bring up that now. Okay, we're now going to jump into our module book. We will start on page 447 of your new book 2 of the module book. Okay, and the previous page looked at a flashlight with a rabbit. I'm not going to do that, but you imagine a flashlight and it will create a shadow that's the same shape but a different size, which helps us think about a dilation. And so we're considering triangle ABC, this white triangle here. And triangle DEF, the kind of pinkish triangle on my screen, and point Y. Imagine that point Y is the flashlight, and triangle DEF is the shadow of triangle ABC. Thus, triangle DEF is a dilation of triangle ABC. Now, if you have forgotten what dilation is, or you never learned because you had Math 8 during COVID, a dilation is a transformation. Okay, we've learned about transformations before. We've learned about transformation. We've learned about translations, where you slide things around. We've learned about reflections and rotations. Those are all transformations. Now, this is a kind of transformation different than those three. Okay, of which of the figure in which the figure stretches or shrinks with respect to a fixed point or center of dilation. Okay, so it's going to get bigger or smaller with respect to some center point, or that's called the center of dilation. Okay, so to get us thinking about this, You're going to draw in with a ruler dy, yd, ye, and yf. Okay, and I want you to measure the lengths of ya, YB, YC, YD, YE, and YF. I would highly recommend that you use centimeters, so you get like lengths of 4.2 or 3.1 or something. Okay, and measure them as accurately as you can. Although we'll be forgiving as far as different lengths. If you measure them differently, that's fine. Okay, we'll get as close as we can with our rulers. Go ahead and pause the video and measure these 6 lengths. Ready, set, go. Okay, when I measure these ratios, and these may be different than what you got, okay, and we'll be forgiving about the numbers not being quite exactly right, okay, and we've disagreed, that's fine too, okay, but YD over YA, when I measured it to the best of my ability, I got 4.2 over 1.6. Now, if you're off by a bit, different than me, I'm not saying that I'm right and you're wrong. That's just what I got. Okay, what I got, put it below so I have more space for all of these. And if I divided those, I get about 2.6. YE over YB, I got 5.0 over 2.0, which is about 2.5. Okay, and then finally, YF over YC, I got to be 4.3 over 1.5. Again, if you don't get the same thing as me, I'm not saying that I'm right and you're wrong. I'm just saying that's what I got when I measured it. I got about 2.9. We round that off. Now, notice that these numbers are kind of close together. If I were to measure these perfectly, and if these actually were drawn perfectly, as a perfect dilation, then what you should see is that these being almost identically the same ratio. Okay, so one thing that we'll notice with a dilation is that the size does change. Okay, these are not rigid motions. Again, translation, reflection, rotation, those are all rigid motions where the side lengths are preserved, doesn't get bigger or smaller, and the angles are congruent. The first thing we notice is that I do not have congruent or the same length as I do a dilation, but there is a certain ratio that seems to be holding, at least approximately the best that we can measure. Okay? All right. Use a protractor to measure the corresponding angles in the triangles. Now, I'm going to kind of cheat a little bit and not use a protractor because I'm, let's not say lazy, let's say efficient. If I look at this angle right here, okay, and if I move this and put it right here at D, it should look very, very similar. That looks close enough for me. And then if I look at angle C right here, move that over here, it should be the same as F, right? So the angles look like they're staying the same. Okay, that's not a very good angle, so I'll draw it like this. Okay, up here. So the angles look like they're staying intact. Okay, so the angles for a dilation are staying the same, but the side lengths are not the same, but they are proportional. Okay, there's a ratio, a common ratio between them that's staying the same. So if I go back down here, they are the same. Okay, a ratio can be drawn with a colon or 2, but we prefer a fraction, or I guess a decimal is also fine. Okay, but they are the same. Okay, if you need to pause the video for students to write, that's fine with me. Okay, number 4, use your measurements in 2, that's the ratios, and 3, the angles, to answer each question about a dilation. How do the measures of the corresponding angles in the image and the pre-image compare? They are the same. Okay, so for a dilation, angle measure is preserved. Okay, doesn't change. How do the ratios of the lengths of the corresponding sides in the image and the pre-image compare? They are the ratios. The ratios, they are also the same. I'll be more specific. Sorry, I'll say the ratios are the same. Okay, so the side lengths are not preserved like a rigid motion, but there's some kind of, the ratios will be the same. Okay, if you need to pause the video for students to write, that's fine. All right, the center of the dilation for this one, the center was point Y. Okay, that was the center of our dilation. Okay, that's number 5, is point Y. And then the ratios you wrote to describe the corresponding side lengths of the original figure and the dilated figure are all equal to the same value. Okay, it was approximately the same, a little different, but that was just because our measuring the best we could, and it was a little different. The value is the scale factor of the dilation. Okay, it's maybe a term you've heard before, maybe not. It talks about, it's the scale factor, it's the ratio between the two things that are similar to each other. Okay, now I want to give you right now that the scale factor, the variable used, is R. Okay, I think the R comes from the word ratio, but for scale factor, the variable that's always used is the variable R. Okay, and I'll give you the formula for scale factor right now. It is an image length divided by a pre-image length. Okay, and this can be any length in the pre-image and any corresponding length in the image. Okay, so let's keep that in mind. Let me go back over here to our triangles. And notice that these right here that we found before, that YD is the image divided by the pre-image YA. And YE was the image over the pre-image of YB. And YF was the image divided by the pre-image of YC. So all of these we just found before was this image over pre-image. And if it helps you, those are in alphabetical order, that the I is over the P, the image length is over the pre-image. Okay, so with that in mind, let's go to the next page. A dilation can produce an enlargement or reduction or a congruent figure. So these are 3 things that can happen with a dilation. It can get bigger, it can get smaller, or it can stay the same, right? So yeah, so just a dilation can be the same or bigger or smaller. For example, when you pinch and zoom on a tablet computer, you can create dilations. I know that typically you can also rotate it as well, and you have some flexibility in how you change an image or something on a tablet. Okay, we're assuming that we're just kind of making it bigger or smaller. We're not rotating it at all. Okay, now consider this dilations on the tablet. Okay, I want you to do A and B. Estimate the scale factor of the dilation produced when you pinch the string to create square QRST. So you're creating the small one. Given the pre-image, that's the beforehand, square LMNP. So you have the big one, you're making it smaller by making the small one QRST. Okay, and I want you to find some pre-image length over a corresponding image length. You can use the sides, you can use the top, you can use like this length divided by this length, okay, or like this length over this length. I guess that's kind of hard because you can't really see where n is, but you get the idea. Any length in the image divided by that corresponding length in the pre-image, okay? And also do B, where you're estimating the scale factor for creating square L, M, and P, the big one, given the pre-image of the small one. So work on A and B. You can pause the video. Okay, so when I measured these, I went kind of the same way that we did the flashlight problem, and I measured this to have a length of 1.8 centimeters. Okay, and I found this to be a length of about 0.9 centimeters. Okay, so I'll be using those lengths when I do it. If you did a side of the triangle, that's also fine as well. You should have similar, ratios that are close to mine. Okay, but that's what I'm going to be using when I do my measurements. Okay, so let's remember that the scale factors are, and that scale factor is something in the image, a length over a pre-image length. Okay, for this one, the image is the small one, and so it's 0.9 centimeters over the pre-image, the big one, which was 1.8 centimeters, and I have a scale factor of about 1/2 or 0.5. Okay, and for B, again, the scale factor is image over pre-image, even though I'm switching the two. This time the image is the 1.8 centimeters, and the pre-image is 0.9 centimeters. Here we get a scale factor of 2. Okay, now let me point out that in A, we got smaller, which is called a reduction. Okay, and in B, it got bigger, which was an enlargement. Okay, so let's just keep that in mind. If you need to pause the video to just write things down, that's fine. So let me erase and scroll up. Okay, number 7. How does the image compare to the pre-image for each given scale factor? If the scale factor is between 0 and 1, then what that's going to result in is a reduction. Okay, that's what happened for letter A. Okay, it got smaller. Okay, and this goes back to the tie-in with the warm-up that I gave you. Okay, whenever you multiply by a number that's between 0 and 1, the number gets smaller. Okay, so that's what happens with a reduction. If your scale factor is between 0 and 1, it gets smaller. Okay, if the scale factor is bigger than 1, it's an enlargement. And that happened with question B. Okay, it got bigger. Again, if you multiply by numbers bigger than 1, 2, 3, 4, right, it gets bigger. Even 1.5 gets larger. Okay, we saw that with 6B. Okay, now it's not asked here, but I'm going to ask it. If I asked about C and I said equal to 1, then we might guess if you multiply by 1, 4 times 1 is 4. It stays the same. This is actually when it's congruent. Okay, so even though we don't think about a dilation scale factor of 1, but you can, if your scale factor equals 1, there's no change in the size. It's congruent. Okay, so on the next page, we get the definition of similar figures. Okay, similar figures are geometric figures where all pairs of corresponding angles are congruent. Okay, we've seen that already. And the lengths of all corresponding sides are proportional. Okay, so that's similar figures. We have congruent angles and proportional sides are similar figures. Okay, very connected with the idea of a dilation. Okay, dilations produce similar figures. All right, now in number 8 is a good problem, but technically by our definition, I have to measure all of the sides and all of the angles, and so this star looks a little bit daunting to me. I don't want to measure all the sides and all the angles of the star, and so I'm just going to skip the problem. Okay, so on to the next page. This is 451. I'm going to go back to read mode. Okay, so using similarity transformations. Now, what are similarity transformations? Well, they are a sequence of dilations and or rigid motions that map one figure onto the other. Okay, so we can use rigid motions, we can use translations, reflections, or rotations, okay, but we can also use dilations, and that would give us similar figures, and that's what a similarity transformation is. Now, I'll be honest that the book for this type of thing is is not precise enough for what I want. Okay, so if the answer key for the book for this, like number 1, demonstrate that the figures in each pair are similar using dilations and rigid motions, they would say reflection and dilation. And that's not precise enough for me. I want you to be more precise. I think high school students can do more than just say reflect and dilate. So I'm going to put in here some extra points so that I can be more precise with my language. Okay, I'm going to call this point C and this point D. I'm going to call this point E and this point F. Just give me some points to work with. Okay, now the way I want you to do similarity transformations is you say what you're doing. Sorry, as you're saying what you're doing to what, okay, and then be precise. If you're doing a translation, along what vector? If you're going to reflect, over what line? If you're going to rotate, what's the center of rotation and what's the angle of rotation? And then if you're going to dilate, I want to know the center of the dilation and then an indication of how much are you like how much bigger or smaller you're going to be. Okay, so I will have that precision as I do this. Okay, and there are more than one way to do this. Okay, so you probably do this in 2 steps if you think really hard about it. I'm going to take 3. I'll take kind of 3 small steps. So the first thing I'm going to do is to translate. Okay, also before I get too far, you can move figure A onto B or figure B onto A. It doesn't matter. Okay, I'm going to move figure A. So I'm going to translate figure A. Let me move up to make sure I have plenty of space. Oh, I can't move this? Okay, I can't move this. All right, translate figure A. Now, you kind of just copy this, draw this over so that I can kind of move it around and translate it around on my board. So here's figure A. Now, I want to translate this, and when I translate, I want to match up corresponding points. I could match up point F or point E, and for some reason, I just like the way it looks when I match up C to D. Sorry, C to E. Okay, so I'm going to say for the translation, along what vector? Along, okay, the vector CE. Okay, and that starts at C and goes to E and stops. So this is figure A prime, just for our records. Okay, now that I have that there, I will then, let's see here, how do I get figure A closer to B? I'm going to reflect. I'm going to reflect over line EF. So I'm next going to then reflect figure A prime. Again, once you do a transformation, you get primes. Okay, I'll reflect figure A prime over EF, line EF. Okay, that's this line right here. Okay, so that is, I'm being precise. If you're reflecting it over what line, I said what line. Okay, now I won't be perfect in drawing this out. I still draw in blue? Okay, whatever. So I'll do my best to kind of just sketch what that would look like. It's going to be bigger. I don't know how much bigger, but something like that. I don't know. It may be too big. I don't know. So this is a double prime. Okay, so it's too big. I'm now going to do a reduction. Okay, And so I need a new color. I want orange. Okay. Finally, dilate figure a double prime from, I need the center and the scale factor, from point E with a scale factor. Okay, I will do image over pre-image. Now, a length that I have to work with in my image, that's where I'm going to, is EF. Over where I started from, which even though I'm going to say DE, DC, so even though I've moved that around, the length hasn't changed, and so I can still use that length, okay? And that's image over pre-image, and that would be a shrinking, and it would put figure A double prime directly onto figure B, okay? Now, I've forgotten to give you the similarity symbol, the symbol for similarity. Now, let me kind of jog over here for a sec and show you that for congruence, we use a symbol of this for congruence. Okay? Now, for similarity, it's just the squiggly on top. This symbol right here means similar. So I will say, so figure A is similar to figure B. If you can see that, I kind of barely fit it on there. Okay, so if there are similar transformations that map one figure onto another, then those figures are similar. Okay, so that was kind of a lot, but that's, you're just getting one under the other using similarity transformations. Okay, for figure B, sorry, for letter B, we have figure A and figure B. Okay, there are multiple ways to do this. Okay, I want you to take your first shot at it. If you want to name a few points, you can. You'll probably need to do some kind of a rotation and some kind of a dilation at least. You can do multiple steps and translate it around if you want. You gotta find some way to map A onto B or B onto A. All right. Now, just so that we all do it the same way, I'm going to choose to go A onto B. Okay, so when I give my answer, that's the direction I'm going, but you could go really any direction if I don't specify. Okay, so go ahead and pause the video. I want you and those around you to see if you can figure out how to map figure A onto figure B and be precise in your similarity transformations. You can pause the video. Okay, so again, I'm going to name a couple of points. I'm going to name this point G and this point H. Okay, no, there's lots of ways to do this. And so if you don't have my method, that's fine. Okay, and this is point I and this is point J. Okay, so I'm going to choose to first do a translation to match up some corresponding points. Okay, I'm going to translate figure A along the vector of GI. Okay, and what that looks like, here's my figure A, pretty close, over here, bing, right here. This is A prime. Okay, I like matching up corresponding points first, so that then that becomes my center of rotation, becomes my center of dilation. Like I have a point that's very clear for me to know where to have my centers of things. Okay, so I have that. The next thing I want to do is to rotate figure A prime. So I will then rotate figure A prime I'm going to go 90 degrees, and I'm going clockwise. Okay, or you could say negative 90 degrees is also correct. I don't have a center. okay, around point I. Okay, so with my rotation, I have an angle, I have a center. Okay, once I rotate that, I'm trying to guess on length. It'll be something like this-ish. Just kind of guessing here. Okay, this is a double prime. Okay, and then I'm going to dilate. Okay, finally, dilate figure a double prime from point I, that's my center of dilation, this point right here, boop, with a scale factor image over preimage. I'm trying to get to a big thing. So that's I, J, divided by where I'm currently at. And even though I moved it around, the length is still GH. Okay, and that would make it big enough to land directly onto figure B. Okay, so figure A is similar to figure B. Okay, so when I taught the other class, I had several students who were doing reflections, and that's fine, okay, because this figure does have some reflectional symmetry. But you have to have a dilation, you have to have a reflection in there, okay? I could do this in 2 transformations, but I figure I would take smaller steps and do 3, and I think it'd be a little bit easier than doing 2, okay? So, hopefully you got something similar to that. Similar, you get it? Okay, I'm going to erase and move on. Number 2, no, I don't like that one. Next page. Use the definition of similarity, okay, in terms of transformations, okay? So technically, the more rigorous definition is that defined with similar transformations, even though it's not how the book defined it a few pages ago, but let's just keep going. Using transformations to determine whether each pair of figures are similar, okay? Now, it looks like triangle XYZ and triangle TUV have the same orientation. Like there's no reflection, there's no rotation needed. They're like sitting kind of in parallel to each other. Okay. Now, even if I didn't have point W, I could connect corresponding points and find that center. Okay, but I'll definitely use it as I can't have a ruler right now. Okay. So those points will connect to point W because that will be the center of the dilation. Okay, so these, if those are all concurrent, then they will be similar to each other. Okay, so this answer is yes, it is. Okay, and the transformation you do is only one, it's just a dilation. And you can go XYZ onto TUV or TUV onto XYZ. I'm not sure which way to see it. I'm going to make it get bigger. So I will dilate triangle TUV from point W with a scale factor. I will do image over preimage, and I really could pick any length that I want. But the one I'm going to use, because it's just vertical, I'll pick this one and this one. Image over preimage would be YZ over UV. Whatever that ratio is the exact scale factor that I need. Okay, so triangle TUV is similar. Now the correspondence does matter, just like congruence. So T corresponds with X, and U corresponds with Y, and V corresponds with Z. Okay? All right. Letter B, do these look similar to you, that it has proportional side lengths and congruent angles? And I don't know about you, but it looks like it's not going to be, right? So this one over here doesn't look as, especially this part down here, doesn't look to be the same angles as this, right? So I don't think that this angle right here, for example, is the same as this corresponding angle here. So I'm going to say no, the corresponding angles aren't congruent. Okay, that's good enough. So I said, well, it's not. If you want to pause the video for students to copy this down, that's fine. Okay, this last one, I could go into depth on this one. If you look at this really hard, it looks like it's supposed to be, and that's because it is supposed to be. There's a typo in the book if you're curious to know. The longest side for this first triangle is right here. Hopefully you agree with that. If you kind of use a ruler and measure stuff, you can. The longest side in this other one, this right triangle, is right here. Okay, now those letters don't match up. So K is fine, but J and L are switched. So the answer key in the book says yes, they're similar, but I would say if that's true, you need J prime here and L prime here. So if you want to switch that in your book, you can. Now, if I had this given to me with J prime and L prime in those locations, then I could do a translation, rotation, dilation, get one onto the other. So they actually do work out, but there's that switch. So I'm not going to do this one, but that's the idea. Okay, so two more things to teach you. Okay, so similar triangles are triangles where all pairs of corresponding angles are congruent and the lengths of all corresponding sides are proportional. We've got that. Similar triangles have the same shape, but not always the same size. Yep, we got that. So I'm going to sketch this out, sketch a diagram of triangle Harry is congruent to triangle Gypt. Okay, so I'll just have it be right triangles because those are easy to kind of copy down. So there's that. And a bigger one like that. Okay, and I'll just name it HRY and JPT. Okay, now the reason I'm doing this one is I want to show you how to list corresponding pairs of congruent angles, okay, and also proportional sides. Okay, so we'd say angle H is congruent to angle J, okay? And honestly, I don't even need the picture because there's correspondence. So the first letter here corresponds to the first letter here, okay? Angle R is congruent to angle P, second letters, or looking at the picture, that's what it looks like. And angle Y is congruent to angle T. All right, those are the congruent angles. Now, the proportional sides one is also a new one for us. Okay, again, you can get this from the picture or the similarity statement, but HR divided by JP is equal to, okay, I'm doing a left over right ratio, RY over PT, so these second two and this second two, is equal to the first and last. So the first and last, so HY over JT. Okay, so if I ask for pairs of congruent angles and proportional sides, then you have that. Okay, the last idea I wanted to teach you has to do with this star picture. That's too much. That's good. Okay, so I want to show you something that happens when you dilate in the coordinate plane and the center is at the origin, okay? This pattern only happens when the center is at the origin, okay? If I pick some point on here, like this point right here, from the center of the origin, okay, the way we did it before was to draw a line with your ruler. Okay, so with my ruler, I can draw this line right here through there and through there and through there and then going. Okay, and then we'd measure the length. Measure this length, okay, and I go that length 3 times, and I have this point right here, right? That's kind of how we do it. If it wasn't on the coordinate plane, we would just kind of measure that. Okay, this point we get right here is the point 6, 9, and this point is the point 2, 3. Okay, now instead of thinking about getting from the origin to that point going diagonally along this red ray that I have drawn here, if you think about it in terms of x and y components separately, like I'm going 2 here, and then I'm going to expand that to go 6, or in the y direction, I'm going to go 3, and instead of going 3, I'm going to go 9. What you'll find is that I can take 2 times the scale factor of 3 and get 6, right? This 2. I take this 3, this coordinate 3, times 3 and get 9. So what I'm saying is you could take the coordinates 2, 3, multiply each coordinate by the scale factor and get 6, 9. Okay? That only works when your center is at the origin. Let's pick one more example point. If I pick this point down here, the point 0, -3, okay? If I draw this line down and I go that distance 3 times, 1, 2, 3, I'm here at 0, -9. Again, multiply each coordinate by the scale factor, and that would give you your image point. Okay, I just want to kind of just let you know that that's a thing, as that might be useful to you later on. Okay, so that's the end of our lesson. I think we've hit all of our objectives that we wanted to hit. The homework is on pages 457 and 458, numbers 1 through 10. If you're in class, then there's an answer key at the back of the room. If you are in one of my students, the answer key is also in Google Classroom. Okay, but try these out. Be very careful on 1 through 4 that you notice the primes. Okay, notice that this is the image and the dark one is the pre-image. Okay, or on this one, this is the image because it has the primes. So notice the primes for the image as you do image over pre-image. Okay, but you have the rest of the period to work on these 10. If you have questions, I will answer them when I get back. All right, we defined dilation as a transformation where angle measures are preserved and side lengths are proportional. We've also defined similar by the same way of congruent angles and proportional sides. Also, we defined similarity transformations as rigid motions and dilations. And we also talked about how similarity transformations give you similar figures. Okay, we talked about scale factor being the image over the pre-image. We talked about how to determine if two figures are similar or not, and also how to use similarity transformations to map one figure onto a similar figure. Thank you so much for watching.